So thank you very much, Professor Bhaskaran, and also Dr. Ganesh for your kind invitation. I really enjoy visiting math science. Of course, I do come to math science pretty often, more to the guest house, but also to the library or conferences in nonlinear dynamics. And a long time back, I mean, we used the math science library as our library because Madras University at that time, perhaps even now, there's not much in the library there. So in my talk today, I want to discuss about the dynamics of Hisenberg ferromagnetic spin chain from nonlinear dynamics perspective. And in particular, I want to point out that this system presents an unending source of integrable and non-integrable nonlinear dynamical systems, which from the point of view of dynamics is highly exciting, and it leads to many interesting results. Which one I use? Or I use my laptop. Electronic one is not working, I think. It's not working. Okay. Okay. So essentially, to give a brief overview of the nonlinear dynamics underlying Hisenberg ferromagnetic spin chain and a source of integrable and non-integrable aspects. So after a brief introduction, I will talk about the basic dynamical equations underlying ferromagnetism, which is of great relevance in applied magnetism. The Landau-Lipschitz-Gilbert equation, LLG equation to start with. But then I will also point out a simple extension of this equation also takes care of what is known as spin torque effect in spintronics, so which has found great relevance in recent times. And then I will point out that there exist many integrable cases. Even you consider discrete chains and continuum versions of these chains. And in the beginning itself, I will point out there are many interesting integrable continuum versions of the ferromagnetic spin chain. But if you consider discrete spin chain, first you find there are integrable maps, XY spin map, XYZ map, and so on. But unfortunately, even the simple isotropic or even anisotropic chain is not an integrable one, but a modified version, which I will point out has some relevance to the continuous limit, the so-called integrable Ishimori spin chain. From dynamics point of view, is completely integrable. Why it's integrable, I will tell. But this also leads to very interesting nonlinear integrable mapping, the so-called Chispel, Roberts, Thompson mapping, QRT mapping, and so on. But these non-integrable anisotropic spin chains in several situations leading to exact solutions and interesting dynamics. And one particular such states are called what is known as internal localized modes. And then when you consider the effect of spin torque, you will see the typical scenario of bifurcations, chaos, and so on. And from the point of view of applications, an STNO, spin torque nano oscillator, is of relevance from the point of view of MRAMs, and then microwave generator, and so on, where a single STNO, the power that can be generated is extremely low, is in the range of nanowatt powers, but one has to enhance the power And we point out that a simple way is to consider an array of STNOs and then use the basic concepts of nonlinear dynamics, namely synchronization of these STNOs, which can enhance the power. Well, there are other interesting aspects, but I don't know what aspects I will be able to cover. But whatever I cover, I will try to point out the basics. So I'm not sure how many of the audience are familiar with the kind of notions I'm going to use, but I'm sure from condensed matter point of view, the systems I'm going to discuss will have relevance. Perhaps the recent motivation to consider this kind of Landau-Lipschitz Gilbert equation and Landau-Lipschitz-Gilbert Slonczewski, that S stands for Slonczewski, which describes the STNO. Albert Fert, who got Nobel Prize in 2007, he says the synchronization of STNOs raises complex problems that are new in spintronics, but is related to the general field of dynamics of nonlinear systems. So from this point of view, so I feel that the study of Landau-Lipschitz-Gilbert equation is of great interest. Well, spin is essentially a quantum entity. So you consider an electron and the spin angular momentum, which is a quantum mechanical operator. But then you consider the Zeeman, consider a Hamiltonian, for example, just the Zeeman term, S dot H apart from constants, and then write down the quantum dynamical equation for the spin momentum, angular momentum. You have a simple equation. Then you take the expectation value of this dynamical equation. So in which case you have a magnetization or magnetic moment per unit volume. You define the expectation value of the spin angular momentum as the magnetic moment or magnetization, and then you consider per unit volume. Then effectively you have a classical variable, dynamical variable with three components, Sx, Sy, Sz. So which I won't use the operator notation, but I will use just the vector notation. But since you have a vector and you can normalize, so you can essentially describe the spin magnetic moment as the unit vector in three-dimensional spin space. So, and then you can show that the dynamics of a single spin, single electron in the presence of an external magnetic field corresponding to Zeeman term is ds by dt, vector ds by dt is the cross product with the minus sign S cross H. Is the evolution equation for this magnetic spin, magnetic moment or magnetization, or I will simply call this a spin hereafter. So you see immediately then it leads to precision. S dot, if you take scalar product with S dot ds by dt, obviously it becomes 0. So the spin length is conserved. So I can normalize it and I can take it as S square equal to 1. And if you consider the magnetic field, again take the scalar product with H. If H is constant independent of time, then you find S dot H is also constant. Is taking a dot product on both sides, you find d by dt of S dot H or H dot S is constant. So the angle between the vector S and H is preserved. So essentially the spin precesses around the magnetic field and so on. So spin essentially precesses when you have a magnetic field, but then the system also admits damping, because for example, if you consider relativistic effect and so on. Phenomenologically, one can add a term which preserves the length, so which for example can have a form like S cross ds by dt. So if you take S dot on both sides, scalar product on both sides, the spin length is conserved, so that you have the dynamical equation for a single spin is ds by dt is minus S cross H lambda S ds by dt, or S cross H, the magnetic field, minus lambda ds by dt. You may call this as an effective field. And so when the damping is absent, So you have ds by dt and s are perpendicular to each other. And when you apply a damping, then you find that the effective field approaches the magnetic field. And this is also a fact coming from the hysteresis experiment and so on. Beyond a critical magnetic field, the spin is uniform, aligns parallel to the magnetic field, and so on. To take into account, again, this factor S cross ds by dt is the appropriate term. And so this is also called Hilbert damping. So you can consider a lattice of spins, a three-dimensional cubic lattice, and then you can write down for the evolution of the spin, the ith spin. It could be the unit vector Si or the lattice vector ds by dt. For example, if you have one-dimensional lattice, you have I1 to n, you can extend this to three-dimensional lattice. So Si, the magnetic field which I wrote earlier, the simple field term, and then you can introduce anisotropic term A with anisotropy parameter A, B, C along the three directions I, J, K, then exchange interaction between the nearest neighbors as I plus 1, I plus 1, I minus 1, and other interactions like dipole interactions or demagnetizing effect, Seilersensi term, and so on. So you have S cross this field, which I will call as H effective field acting on the system, plus the damping term, which I will call as Si cross lambda dsi by dt. So that for the entire lattice, I can write down the dynamical equation as ds by dt equal to minus Si cross H effective minus lambda ds by dt, where Si's are three-component vectors, and each one is a unit vector and so on. So H effective contains H exchange term, interaction between the nearest neighbors, anisotropy, demagnetizing term, other applied magnetic field like this, and so on and so forth. So this equation is without the damping, was originally written down by Landau and Lifshitz in 1935, who also introduced this damping from relativistic consideration phenomenologically. But Gilbert in 1955, from a Lagrangian approach, he introduced this term rigorously, and one has this equation. This equation is the basic equation in applied magnetism to describe magnetization, and this is called Landau-Lifshitz-Gilbert equation. In particular, if you go to the continuum limit, so that the nearest neighbors are close to each other, then you can replace SIT by S of vector r t. So this vector r is spatial coordinate x, y, z, whereas spin itself has three components in the spin space. So you have the partial differential equation ds by dt equal to S cross del square S. This comes from Si plus 1 plus Si minus 1. When you introduce the lattice parameter, expand in the lattice parameter in terms of Taylor expansion. So these are the anisotropic term, dipole term, demagnetizing term, and external magnetic field, and then damping term. So this equation also you can write in this form, and this is typically called Landau-Lifshitz-Gilbert equation to describe the bulk properties of magnetism, ferromagnetism, and so on. Over the years, it has been shown that this equation admits spin waves, elliptic function waves, and in some case, localized waves, solitary waves, they called solitons. Solitary waves, and some cases they are solitons. There is a distinction between solitary waves and solitons, at least in the mathematical physics sense. In one dimension, but if you go to two dimension, you can have vortex-like solutions. In some cases, you have what is known as kermions and so on and so forth. So there are many possible kinds of excitations one can identify in these systems.
Elliptic function waves are periodic waves, but not sinusoidal.
Not sinusoidal. In the limit, elliptic functions are associated with a quantity called a modulus parameter, which for example you call as k square runs from 0 to 1. When k square approaches 0, elliptic function Cn, Sn, Dn, Cn goes to cos, Sn goes to sine, Dn goes to constant 1 value and so on. So in that limit, then you have elliptic function reduces to spin waves. Okay. And the other limit, when the modulus goes to 1, Sn becomes tan h, Cn becomes secant h, and so on. They lead to localized waves. And in some cases, those localized waves under interaction, they can retain their shape and speed except for a phase shift, then they become solitons and so on. Well, the existence of such waves was originally pointed out by myself and Dr. John in a long time back. So you consider an isotropic Hisenberg spin system. I have removed all the constants, I have rescaled them. So you have ds by dt equal to s vector product d square s by dx square with these 3 components and a constraint. So because of this constraint, this becomes highly nonlinear, non-trivial evolution equation. But then associated with this, you can identify 2 linear operators, 2 by 2 matrix operators. So if you define a matrix S with the components of the spin, Sz in the diagonal term Sz minus Z, S plus S minus, S plus is Sx plus Isy, etc. Then if you define the operator L equal to I lambda S and B equal to lambda S Sx plus 2I lambda square, then this so-called lax equation, LT L commutator B is equivalent to ST Sxx. So this is the 2-component form of the matrix form of this equation. So effectively, you have linearized this nonlinear partial differential equation, and then you can carry out what is known as an inverse scattering transform procedure. So you start from the initial data at t equal to 0. With this operator, you get the scattering data, direct scattering, and then you go to this equation asymptotically as x going to t going to plus or minus infinity. This s is supposed to take either parallel to the z-axis up or down. Then depending on the initial condition, this equation LT equal to BL, that takes a very trivial form. And from that, you can find that time evolution of the scattering data and carrying out an inverse scattering transformation by solving a linear Volterra type integral equation. You can solve the Cauchy initial value problem associated with this partial differential equation. So it's a completely integrable system. In fact, this equation has a Hamiltonian description. The Hamiltonian can be written as a sum of 2 kinds of terms, one corresponding to discrete states and the other corresponding to continuum states. But then this transformation to these new coordinates is a canonical transformation, and the equation you can trivially reduce to in terms of action angle variables, and so this becomes a completely integrable dynamical system. From a different point of view, this equation is also geometrically or gauge equivalent to the again soliton possessing nonlinear Schrodinger equation, which I showed from a geometrical perspective by defining, since you have an one-dimensional spin system, which you can consider as a curve in the spin space, and the spins are all continuously situated. So you can describe a curvature associated with this curve, so which I call as kappa square Sx dot Sx, and torsion is 1 over k square S dot Sx cross S double x. And with this definition and defining a non-local transformation of this form, then I can show the spin system is effectively equivalent to this nonlinear Schrodinger equation. And this is also a gauge transformation. And so this gauge connection between spin system and the soliton processing system is a very important concept which has been found to be useful in generalizing these ideas to other situations. For example, if you include a single site anisotropy, these are all in one spatial dimension and their time evolution, then in that case again you can gauge transform to a nonlinear Schrodinger equation which is equivalent to this equation. So this is also an integrable system. Biaxial anisotropy, for example, if you have this Js is J alpha S alpha in alpha. So that is also completely integrable soliton system. And I showed that in the limit lattice parameter A tending to 0, I got this isotropic case and so on. But you can also go to the next orders and so on. And these equations are also found to be again integrable using these geometrical notions and other things. But I will not go into the details.
You mentioned about this gauge transformation. Is it possible to visualize this in terms of spin variables? What are the gauge transformations?
Yeah, the gauge transformation I talk about is if you transform this matrix S I wrote earlier. This to some G S G inverse where matrix transformation. Then you can show that in the transformed frame the equation looks like this. So that's the kind of gauge transformation. So there is a this equation is called zero curvature condition, and that condition is maintained, and so that's a gauge transformation in that sense. Yeah. So this can be generalized in different way. We have done in many generalizations of that. It is also of interest to extend this to 2 plus 1 dimension. But unfortunately, in 2 plus 1 dimension, the straightforward generalization, for example, the Hisenberg spin chain, just S of t equal to S cross Sxx plus Syy, that is not integrable. So we have proved by, there are methods to prove now which have been developed recently. But then there is one interesting transformation which is essentially a non-local form of this Heisenberg spin equation. So you have S vector product Sxx plus alpha square Syy plus you introduce a scalar field Ux Sy plus Uy Sx. Then U itself satisfies it's not an evolution equation, but it's a scalar potential, one can say. It's a potential equation it satisfies, as if the energy is injected from infinity into the system. So that kind of system has been shown to be completely integrable in 2 plus 1 dimension. There are ways of proving how the integrability arises. But it is also geometrically and gauge equivalent to 2 plus 1 dimensional so-called Davis-Stewartson equation, which is an extension of the nonlinear Schrodinger equation. So just like a space curve moving and its evolution you consider for 1 dimension, you can also consider a surface moving, and you can consider the underlying surface equations, the so-called Gauss-Weingarten equation and its compatibility condition, etc. Then you can get this equation. So in that sense, this is also a completely integrable system. But we have also shown even a long time back that if you consider damping also, you can map to damp the nonlinear Schrodinger equation and so on. You can develop perturbation theories to understand these kind of systems, etc. You can also show that these equations arise from a Hamiltonian formulation. So you consider an undamped spin chain with the Hamiltonian, so corresponding to anisotropy A, B, C, and on-site anisotropy external magnetic field. You write down the quantum Heisenberg equation of motion associated with this equation, and then take the S infinity limit to obtain a semi-classical or classical dynamics of this equation. So you can get the underlying spin evolution equation, or start with beginning itself spin Poisson brackets. SI Poisson bracket equal delta ij Kronecker delta SI gamma. This definition then also you can with the same Hamiltonian. So, where Poisson bracket of two spin functions A and B are defined in this particular fashion. So, it satisfies all the Jacobi conditions, so that you can write down the equation of motion for the spins. Now, spin vectors in this form. So, SI, the nearest neighbors SI plus 1, SI minus 1, the anisotropy terms, and then on-site anisotropy magnetic field, or any other form of H, you can write down the underlying spin evolution equation and so on. So, if you want to go to the continuum case, SIT I write as S of RT, where R as 3 spatial coordinates, then the nearest neighbors are S of RT plus A dot del S A square by 2 del S, and then take the A tending to 0 limit in the equation of motion. Then you can get the underlying continuum partial differential equation for the spin, or you can also define spin Poisson brackets for the field spin fields S of alpha T, S beta of T, S epsilon alpha beta gamma S gamma, and then write down that evolution equation, variational equation ds by dt is delta H, the functional derivative delta H by delta S, where H is the Hamiltonian functional. So, then you can write down the equation of motion. So, that is general Landau-Lifshitz equation in the continuum limit and in the discrete case and so on. There is also an interesting way of looking at these equations because of the condition constraint S square equal to 1. So, you have a 3-dimensional evolution equation, but constrained by one condition. So, you can remove this condition by going to appropriate coordinates. For example, you can go to polar coordinates, but then that makes the equation very complicated. But there are other interesting description I showed curvature and torsion, through which I defined a complex variable Q, which resulted in nonlinear Schrodinger equation and so on. There is also another interesting possibility. You can stereographically map the spin variables onto a complex plane. So, you have the spins S, then you try to map it onto stereographically on a complex plane omega, it's Sx plus Isy by 1 plus Sz, or Sx has this form omega plus omega star 1 plus omega star, Sy this and Sz this. Then the evolution takes rather nice form in the sense that suppose damping is absent, you have just I omega t plus del square omega, and then there is an additional term 2 omega star del omega square by 1 plus omega star, and then this is anisotropy terms, etc. Then this is magnetic field. I have also introduced Jx, Jy, Jz in the next transparencies. I am going to consider the effect of spin current, and that if you include that spin current, they occur along with this magnetic field. So, I am going to point out that the spin current is effectively a magnetic field, but complex now in this case. So, that has important consequences. And then you also find that this damping, the entire damping term occurs as a coefficient modifying the time derivative term. So, instead of I get I into 1 minus I lambda. So, that is the only change. So, in order to, if you want to consider the spatiotemporal patterns the spins can admit, it's fairly interesting to use this particular formulation. Okay. So, this is another interesting formulation of a spin. So, in the discrete case again you can define the stereographic variables, and then the system takes a particular form which will be again useful to consider discrete integrable systems, but I am not going into those details. Now, consider the effect of spin current. So, what is this spintronics or spin angular momentum transfer effect? So, when you consider tri-layers of nanomaterials, you know that the GMR effect. giant magnetoresistance effect. So, in 1996, this person, Slutsky, working at Bell Telephones, I think, he wrote a very famous paper in which he considered a system of tri-layers, 2 layers, 2 outer layers are ferromagnetic materials like cobalt, and then there is a or copper, and then this is cobalt, and then there is a spacer in between which is conducting but non-ferromagnetic. So, you have cobalt, copper, cobalt material, and you also find that this is a nano material of the order of 40 to 100 nanometers, and this is again a small spacer, and this is of the order of 2 to 4 nanometers film size. Okay. And then you have the outer conducting materials. So, actually this is a 5-piece nano material. So, you consider the quantum dynamics underlying this equation. You actually write down the Schrodinger equation corresponding to this kind of one-dimensional wire. So, you have 5 pieces.
For the conduction electron.
Yeah, for the conduction electron. So, the electron flows in this direction. Okay. And then, since this is a ferromagnetic material and the electrons which are unpolarized in the sense that the spin directions could be anything, when they pass through this larger ferromagnetic material, they tend to get polarized. Okay. And then since this spacer, the spin diffusion length of this spacer is small, the size of the spacer is small compared to the spin diffusion length, then you expect the spin directions do not change much, and they pass this spacer, and then they interact with these the spins of this outer film, which are free, and this interaction is essentially leads to a torque. So, this you can show quantum mechanically. Semi-classically, Slutsky had shown by considering this as a 5-piece one-dimensional material. You look at the WKB wave function of these 5 pieces. The outer 2 are not important. What you are interested in is the spins that pass through this layer and then this layer, and see how they are interrelated, the influx and the outflux. So, considering that, you can show that the underlying effect is essentially a spin torque, as if these spins induce a torque on these spins, free spins. So, the effect of the spin current is essentially a spin torque effect corresponding to.
Will be on the cobalt spins, on the magnetic
Yes,
spin.
yeah, on the smaller thin film, okay, thin film of that. So, what essentially one finds is the effective evolution equation for the outer spins, the free spins, is ds by dt s cross h effective minus lambda ds by dt. This is nothing but the Landau-Lipschitz equation corresponding to the ferromagnetic film, and the effect of the spin current is just s cross the current. Okay. But this current comes from the spins, and which are polarized, and you can and Slutsky has shown that effectively the spin current has a sp, the polarized spin, and then you have some polarization function plus 3 s dot sp. But compared to 3, this can be effectively neglected. So, you have essentially a constant vector here sp. So, the effect of this spin current is just s cross the sp, the fixed spin. So, if you want to understand how this tri-layer nanolattice works, you have to essentially understand this particular equation. So, this is called Landau-Lipschitz-Gilbert-Slutsky equation, LLGS equation. And one can show that the effect of this spin current is to essentially change the direction of the spin on the outer layer, or it can make the spin to precess at a frequency and the range of microwaves. So, effectively this one-dimensional arrangement, a nanowire or a nanopillar or a nanowall or a spin wall acts as a generator of microwaves, a microwave generator. Okay. And one can show that the power that can be generated from such an arrangement is low. So, otherwise it has a lot of nice properties. The power that is generated out of this is extremely low, it's in the order of nanowatts. So, the question then arises how to enhance the power of this generator.
So,
Yeah.
if I understand correctly, that spin current mimics some kind of magnetic field and
Yeah.
generates Lorentz precision of the power.
Yeah, so that's what I have earlier said. So, if you write the Landau-Lipschitz-Gilbert-Slonczewski equation in the stereographic form, you find the effect of the spin current is to simply change h to h minus ijx, j to hy to this form, and hz to this form.
So, even if you don't have external magnetic field, there is an effective magnetic
Yes. So that is the arrangement that it happens. And you can see that if you look at how the energy acts, dE by dt, the energy functional you already know from the H effective form, then you find that is minus lambda st square and plus the spin current term. If the spin current term is absent, it's damping, because lambda is positive, the damping constant, mod st square is a positive definite function. But because of this, energy is not necessarily decreasing along trajectories, so novel features may arise. So that's what happens, and so these are the Slonczewski's form and so on. Typically, you assume that in the film, in the cobalt film, the thin film, the spins are homogeneous. That means spatial variations you neglect, in which case you have a single domain. So each spin, all the spins are evolving identically. So, for example, if you write down the evolution equation in stereographic variable, then you have this equation 1 minus I lambda omega t plus the current terms and the magnetic field terms, and these are anisotropy terms, A omega minus B omega 1 minus omega square. These are effects arising from the shapes, demagnetization terms, N1, N2, N3 corresponds to, for example, if you have a sphere, they are all equal, if you have a plane, one of the variables is 0, etc. So you can also analyze this numerically. But even simpler one, you consider an isotropic sphere as an example. So isotropic means all these things vanish. You have effectively 1 minus I lambda omega t is jz plus I hz omega for appropriate magnetic field. So you can trivially integrate, and you find omega t is omega 0 exponential minus lambda j minus lambda hz into t, and then exponential of minus I into this. So this one corresponds to precision, and this one corresponds to damping, which can switch the direction also. So one can easily see that that the spin current can switch the direction of the magnetic field. So for example, if you apply purely magnetic field alone, then you find that the spin initially the spin is here, and it takes a long time to precess and then to change its direction. But if you apply the spin current alone, there is a faster switching from this direction to this direction. So you can use this as a switching device, but more interestingly, if you have the other anisotropy and demagnetizing field, etc., we can use this as a microwave generator. So many other effects can be studied by introducing this.
General question.
Yeah.
Earth's magnetic field also switches over 10,000 years.
Yes.
There is also supposed to be a dynamical phenomena involving currents and coupling.
Yeah.
Any relation?
Well, these are at the nano level and gigahertz range. But where is the phenomena you are talking about is in an extremely long, large scale. So I don't think that that it will have any effect or any similarity between this effect as far as I understand. Okay.
What's the long-term behavior? So you take the
No, the small one is not polarized. The small one, originally the spins are in random direction. Only when the polarized spin passes through the small film, there is a torque. And because of this torque, then either they switch directions or they precess, depending on the strength of the incoming current.
So it can precess for a while and then suddenly switch.
No, I mean it can happen. It can switch, for example, from this example. So that is one possibility. But it can also induce self oscillation because it's a nonlinear dynamical system. It can induce self oscillation, and it can also introduce bifurcations and chaos. For example, typically, so I've plotted DC current. So the current, suppose the spin current is DC, you can also apply AC current over that. And this is one of the magnetic direction, MX direction. So you find up to certain critical field, you have single limit cycle oscillations, and then you have period double, 4, etc., etc., and then you have even chaotic situation and so on. So you try to operate your, it depends on what purpose you are using. If you want to use for microwave generation, you will be perhaps using in this direction, in this range, or even in this range. But if you want to use this for other purpose like secure communication, etc., so chaotic secure communication, so you can use this, etc. So there are interesting dynamical situations. But if you want, I said that one of the negative aspects of this STNO is that extreme low power. How to enhance this power? So for that, I will try to identify many such or keep such oscillators. So this is one typical circuit. So I can keep many such devices, nano devices, and then connect them serially or parallelly or in a hybrid sense. There are many other possibilities. Couple them appropriately. And then I can also show the under coupling under appropriate conditions, the power can be enhanced. And the power can be enhanced of the order of n square. So it's quite possible because in a typical experimental situation, they say if it is a microwatt range, then it's practically useful as a microwave generator and so on. So it is there are possibilities of using. Already people have experimentally identified 5 such nano oscillators can be synchronized and so on. So as technology improves, there is a possibility that this can be enhanced and so on. This is not an integrable system with anisotropy, etc., coming in, even a single spin, okay, because it shows bifurcations, chaos, and so on. So when it shows that kind of thing, it's not an integrable system. But there are many interesting regions where you have oscillations, self-oscillations, or period doubled oscillations, etc., or chaotic regions. So each regime can be used for different purposes, depending on the situation. Now, in the remaining time, I will very quickly go through what is this, what else can be said about the discrete chain itself. So you consider an anisotropic Hisenberg chain with different even nearest neighbor interactions with different strings, and then on-site anisotropy, external magnetic field. So you can write down the evolution equation for the spin vector or the components in this particular form. The first thing I want to point out, you write down the evolution equation for the 3 components. So they are a little bit complicated, but you can write down. But if you try to confine the spins to a plane, say xy plane, so that SI z equals 0, then you find the dynamics become statics. So because if you look at this equation, suppose I take Sz as 0, then the left hand side is 0, right hand side, this will be equal to 0. But look here, here Snz is 0, here you have Snz, here you have Sz, here you have Sz. So these are all these things vanish, and so this is a constant. You can take that to be 0. So essentially, you have a map. So the evolution equation becomes a map of this form. In particular, if you consider a magnetic field absent, then you have this map with the condition that SIX plus SIX square, sorry, square is missing, SIY square equal to 1. So this is the evolution equation now you have. It's not evolution equation, it's a spatial variation equation. Okay. Now the Hamiltonian is given for this particular form. In addition to that, you can always deduce, well, this equation also admits interesting solutions. One can write down in terms of these elliptic functions, spatially varying solutions, okay, where dn is, well, this k is related to this quantity, so I am not going into that. And you can write down the total energy, etc. And in the limit form, you have tan h, and this is secant h. So you have a localized structure, but then it also admits a first integral, because this is a two-dimensional system effectively. The spin system, you have a Hamiltonian, and then you have I show that it admits a first integral of this form. So to prove that, you take that resultant spatial variation equation, which I wrote earlier, multiply this by Sn plus 1x, Sn minus 1x, and Sn plus 1y, Sn minus Sn minus y, and then use the condition that Snx square plus Sny square equal to 1. Adding these two equations, then you can prove that that this quantity into this quantity, Sn plus 1x, Sn minus 1x, etc., 0. This is not always 0, so this is ultimately equal to 0. Effectively, you can rewrite this as b Snx, Sn plus 1x, a Sny, Sn plus 1y, which is equal to b Sn minus 1x, Snx, and Sn minus 1y, Sny, which means if you replace n by n plus 1, you get this one. So this is invariant. So this is an integral of the system. So the equation, the map is integrable. So integrable, nonlinear integrable maps have evolved from these studies, this kind of studies. In fact, one can show that in a simple terms, if you go to polar representation, Sn equal to cos theta n sin theta n, and you can rewrite that spin equation in this particular form, and defining xn equal to tan theta n, you have a map of this form, a nonlinear integrable map. So this is a simple example of what is known as QRT map and so on. You have an 18-parameter integrable map. A special case of this is this two-dimensional system. Similarly, if you consider a three-dimensional integrable system, then you find that you have this system of equation with this spin constraint, and you have the Hamiltonian, where the Hamiltonian is written as a Sn x Sn j Sn plus 1 means a Sn plus 1. So a Sn x Sn plus 1x plus b Sn y Sn plus 1y, etc. Then one can show that there are two integrals this system admits besides this. One is since you have this static equation, you can write down since Sn cross something is equal to 0. So you can define a Lagrange multiplier, Sn plus 1 equal to Sn minus 1 of this form, and multiplying both sides by a term like Sn plus 1 minus Sn minus 1, you can show that this is an integral. That's trivial to see. But I also want to point out there is a second integral for this equation. So considering this equation, I have rewritten this in this particular form, and multiplying this, squaring both sides, where I call j Sn. J means j operating Sn, you have this anisotropic form. So squaring that on both sides, rearranging in particular form, I can show that as before, an plus 1 square mod an square an plus 1 Sn square is an minus 1. And you can see that if you change n to n plus 1, you get the left hand side. So that means changing n to any value, you have exactly the same form. But the original equation is satisfied. So you have also a second integral of motion. So that means the system is completely solvable. In fact, you can, this admits again interesting solutions. One can prove that we have shown that this kind of solutions exist. Cn, Sn, Cn, Dn, and their limit forms tan h, secant h, secant h. So you can plot this kind of excitations, localized excitations exist. And they are also stable. So you perturb and go to a dynamical equation, they are stable and so on. So you have these integrable maps. The study of these spin systems also leads to integrable nonlinear maps. So that is a field of its own. It has developed many such integrable systems have been developed.
What is the definition of an integrable map?
Yeah, so integrable map, if you can show, if it's a two-dimensional integral, if you can show two independent integrals. So independence comes from if you have W1, W1, W2, then you write find the rank of these quantities. Then if it's if the rank is non-zero, then you can show it's the integrals are independent, and the system can be solved. You can prove, no, depending on if it is a two-dimensional map, then you have two integrals. If it's a three-dimensional map, you have three integrals, and if you have an n-dimensional map, you have n independent integrals. So once you have these integrals, there is a possibility that you can also find the solutions exactly, completely, and so on. Okay. So that's the integrable map system. Well, you can ask the question whether there are integrable spin chains. So even the simplest case, the isotropic case, the spin chain, dsn by dt equal to Sn cross Sn plus 1 plus Sn minus 1. This is not integrable. Okay. You cannot even, as far as you know, you cannot even find any exact solutions for this equation, except trivial solutions. Spin half is integrable, but the classical spin in some sense is, corresponds to S going to infinity, S very long value. So that's not integrable. But these nonlinear evolution equations can play a very tricky role. In some sense, you can expand a finite spin system in terms of spins. You can add corrections, etc. So when you add those corrections, they may become non-integrable in some sense. Okay. So this is not integrable. But if you consider, if you make a small change in this evolution equation, instead of Sn cross Sn plus 1, if you introduce this additional term, similarly Sn cross Sn minus 1, you introduce this additional term. So Sn dot Sn plus 1 and Sn dot Sn minus 1. This equation is completely integrable in the sense I can find a lax pair and solve the initial value problem. So you take ln, this operator ln and this operator mn, and then ln dot dln by dt is commutator of ln mn plus 1, something like that. If you do that, then you get the Ishimori equation. But the interesting point is that this system corresponds to a Hamiltonian, not of Sn dot Sn plus 1, but log of 1 plus Sn dot Sn plus 1. It's not polynomial, but if you expand this, the first term is Sn dot Sn plus 1. That is the Hisenberg spin chain. But if you couple the higher order terms in this particular fashion, then the system becomes integrable. So that's the way the spins behave like. So you have the exact solutions and so on. There are a lot of interesting properties. Perhaps I will skip all that. Then another interesting point is that in this spin system, if you introduce this kind of parameterization, cos phi n, cos omega t, cos phi n, sin omega t, sin phi n, then you end up with this map. This is one of the 18 parameter integrable QRT map and so on. Okay. That's the system. Well, there are a lot of further results on non-integrable cases. In the case of anisotropic Hisenberg spin chain, which we have recently deduced in the past 10 years and so on. Perhaps I have 5 more minutes. Yeah, I will quickly sum up all this. So I have so many other things. So one way of looking at this system is to look at appropriate representations. So as you have seen that these are nonlinear systems, solutions occur in terms of elliptic functions and so on. Though these are not integrable in completely integrable in the sense, if you have an n-dimensional system, you have n involutive integrals of motion existing or not. That may not be possible, but still you can find exact solutions. And then if you know exact solution, you try to look at their stability, at least linear stability, how stable they are in the parametric regime where these solutions are stable, etc. So from that point of view, I try to look at these spin variables and try to represent in terms of appropriate functions. For example, looking at the solutions of the Lamé equation. The Lamé equation is an eigenvalue problem with a potential involving these elliptic functions, okay, in a particular form. You can show that they have interesting solutions proportional to S1, Cn, Dn, etc. They are more higher order forms, etc. So you can try to look at even more general cases. I will not go into the details. So for example, if I look at solutions like Sn equal to alpha Sn Pn. So n corresponds to the site, P is the momentum, and minus omega t plus a parameter. This k is the modulus of the elliptic function. Similarly, Sny is beta Cn, Snz is Dn. And then substitute into the evolution equation, and then equate the coefficients on both sides using the properties of the elliptic functions, because you can take the derivatives of these elliptic functions, etc., on both sides, and then you find that there are constants on both sides and equate them. And if you equate that, then you get interesting structures. For example, if P is 4 capital K is a complete elliptic integral. I'm sorry, I cannot go into the details, but elliptic integrals are associated with, so you have an integral d theta by root of 1 minus k square sin square theta 0 to pi by 2. So these are all known quantities. So for that form, I have a non-trivial dispersion relation, and I have exact solutions. And these solutions look like these particular forms. Okay. And similarly, I can have these can be semi-classically quantized, and you can write down the corresponding quantum spin, quantized relations. You can also have other kinds of solutions like this, which are spatially varying. For example, two alternately varying spins, but each one is oscillating in this elliptic function way and so on. So there are limit forms and so on. So many such exact solutions can be obtained even in the presence of magnetic field. Again, you have modified functions like this, and their total energy you can find. So these solutions also depend on the site. The total energy depends on the site, so that leads to what is known as Peirce-Nabarro potential barrier, etc. So many interesting results can be obtained. Just in the last 1 minute, I also point out that these kind of nonlinear lattices can also admit what is known as internal localized modes. In the sense, you can have solutions which are localized, but they don't move, and they can oscillate around those points and so on. So such motions have been identified for a particular kind of magnetic chain, And here numerically, here we point out that you can find exactly such solutions. For example, you can find solutions where only one spin oscillates, Si, Xt, Sy, Zt, Sat. Then you have this evolution equation, which can be rewritten in terms of, well, you can modify this. You can find the exact solution in terms of elliptic functions. So, one spin where only n spin is excited and the remaining spins are constant. Similarly, you can try to extend this to two spin excitations, Siz, Si plus 1z, and you can solve the resultant equation. You can reduce, you can obtain exact two spin solutions, etc. Similarly, you can extend this to three spins.
Are those solutions stable in time?
Yeah. So once you get these solutions, you also try to look at, well, these are three spins. You can also look at their linear stability, and you find there are certain regions of the parameter space where these solutions are stable. So they do exist, and so on. So you have to, that you have to identify numerically, and so on. Okay. Perhaps I think I've come to. I think my time is up, and I will not go into the further details. I will only come to the end of my talk. So I'm not talking about the synchronization aspects of these STNOs and so on. There are very interesting aspects that are involved. I will only conclude by saying that the topic of dynamics of Heisenberg spin chain is an unending source of nonlinear dynamical systems. I have tried to quickly point out the type of integrable and non-integrable systems one can encounter by studying this Heisenberg spin chain, integrable maps, ODEs, PDEs, etc. And there are also very interesting non-integrable systems exhibiting bifurcations and chaos. So what has been understood so far is only a tiny part of the general system. So as you might have looked at, many more exciting problems remain to be tackled. Thank you very much for your attention. Experimentally, yeah.
Now, if basically added, it will be 5 units of power, but it can go up to 25.
Yeah, slightly below that experimentally.
Realized value.
Pardon?
What is the value that has been realized in the lab?
The power.
Yeah.
Yeah. So I do not exactly remember, but so the normally the power of a single STNO is in the order of nanowatts. So that into 25 times. So one order it increases. So if we can do this for so 200 or 500 such oscillators, perhaps the power can come in the micro watt region.
No, if the power for one STNO, let us say 1 nanowatt. Now for 5 it can go from, I mean, achieving 5 nanowatt for 5 STNOs is trivial, but with the interference effect it can go up to 25. So what is the efficiency achieved? Maybe 10 or 15 or 20. 25 will be very ambitious.
No, it's the experimental results shows that it's slightly below. Subhas, you remember? So that's what that figure shows.
Really very high.
You said that some systems can be shown to be non-integrable.
Not shown to be. Most of the systems are non-integrable.
But
integrable systems are measured 0. Okay. Yeah.
So you cannot say a particular system does not have integrals of motion, or
Well, now we have
Techniques
now we have methods to identify whether a given system is integrable or not in certain sense. So we have not what is known as singularity structure. You look at the evolution equation and you try to look at the structure. So there is a major difference between linear differential equation and nonlinear differential equation. Nonlinear equation per se, they can generate singularities on their own. So just look at dx by dt plus x square equal to 0. So this will have, if you integrate this, you will have solution like 1 over t minus t naught square or square root or something like that. T naught is arbitrary constant of integration. So the singularity can be placed anywhere in the complex plane. So like that, you look at how the integrable systems have their singularities placed, and non-integrable systems have their singularities placed in the complex plane. So you do find that all the integrable systems have some nice structures. For example, this elliptic function, their singularities are on rectangular, the edges of rectangles. Okay, the poles are located at the rectangles. But if you look at typically no non-integrable system, the singularities are situated in a very complex pattern. They are self-similar in structures, order within order, or disorder within disorder, or something like that. So one tries to look at the structure of the singularities. You can come to some conclusion that the given system is non-integrable and so on. But in this spin system, there is additional complication. You have for each spins, there are 3 components. There is a constraint, sx square plus sa square plus sz square equal to 1. So that also you have to bring into your calculation if you want to show a given spin system is integrable or non-integrable. So there are further difficulties in dealing with that, but there are ways to look at. Now it has been developed, and people are also developing it further.
So it's not an easy task.
None of them is an easy task. You have to work hard. Typically, nonlinear systems are classed by themselves. Each equation poses new difficulties, but you have to investigate.
I have one question. You showed when localized excitation. Very interesting, because in some quantum models, if you give a typical quantum model, they will be always propagating excitations like block waves. But then sometimes there are excited states which are called flat bands. They don't disperse with momentum.
Okay.
So a way of saying is that they are infinitely heavy.
Okay.
So you can create some superposition, and then you leave it there, it will just stay there and it oscillate.
Okay.
So what you find seems to be analog of flat band excitations that occurs in some frustrated spin system.
Okay.
Maybe we should discuss
Yeah.
this. Very
Yeah. So
interesting.
these are anisotropic system with a magnetic field, so they may have relation to what you say.
If there are no further questions, we thank Professor Lakshmanan once again.